where is concave down. But now we want to know it exactly, right? And the changes between concave up and concave down will be at the points where the second derivative is equal to 0, right? So we have computed the first derivative of this function, which is 12x cubed plus 12x squared minus 24x, right? And we have studied the first derivative, as it should. Now let's calculate the second derivative of this function. And so 12 by 3 is 36 x squared plus 24 x minus 24, right? So we can factorize out 12, right? We can factorize 12 and we get 3 x squared plus 2x minus 2, right? So now we want to see whether where the function is equal to 0, right? And because that would be they would be the points where the function stops being concave up and gets concave down, or vice versa. So we set that equal to 0. And of course, we dispose of 12 because 12 is not interesting to us. It's a positive constant, right? And so we solve for x, and now we use the quadratic formula again, right? X equals minus b plus or minus the square root of b squared minus 4ac, so is minus 4. A, which is 3, minus 2, which is C, divided by 6, right? So that gives us minus 2 plus or minus the square root of what? We have 4, 8, 3 by 8 is 24 plus 4 is 28, divided by 6, right?
Right.
Makes sense. So 24, 28, yeah, okay. So now we can simplify this number a little. So we have minus 2 plus or minus, so 28 we can write as 4 by 7, right?
Yes.
And we can take out 2, 4 from the square root,
the
right?
square root of 7.
So square root of 7 divided by 6. So we have, 2 solutions. One is minus 1 plus the square root of 7 over 3. And the other is minus 1 minus the square root of 7 over 3. Right? So one solution is positive. And now that we have the graph, we can figure out where these solutions are, right? So we have the graph, right? The negative solution is going to be somewhere here, right? So we can, calculators, you don't use the calculator, but you can have an idea of what the point is, right? Because if instead of 7 we had 9, right? You can think of, instead of having 7 to have 9, then that would be minus 1 minus 3 divided by 3, so minus 4/3, right? It's a little bit, right? It's a little bit more than, less than minus 1. So here is the negative, inflection point, right? And it fits really nicely on the graph, doesn't it? Right? If it was in a strange point of the graph where you don't think that there could be an inflection point, then it means you are making a mistake, right? And the inflection point on the other side is square root of 7 minus 1 over 3. So again, square root of 7 is a little bit less than 3 minus 1 is a little bit less than 2 divided by 3 is between 0 and 1, say, right? Is some number between 0 and 1. That's all you need to know And so it would be somewhere here, right? That is where the function transitions from being concave up to being concave down and vice versa, right? All right. Again, if we want to verify the story, we want to make sure that we are doing right, we can, do the test points also for the second derivative, right? The test points are not just something that belongs to the first derivative. You can use them for also for the second derivative. So we have square root of 7 minus 1 over 3 and minus square root of 7 minus 1 over 3, right? These are the two inflection points, and we can pick up the test points and then now we plug into the second derivative, not the first derivative, right? So we can pick up 0, for example. I just told you that this point is less than 1, right? Even if you don't know exactly the value, but you can see that, square root of 7 is between 2 and 3, so minus 1 divided by 3 will be less than 1. So we can pick 1 as a test point here, right? And we can pick minus 1 as a test point, or minus 2 if we want to be safe, as a test point there, right? Right? Now, if I plug 0 into the first derivative, I get negative 2. And now, what does the minus 2 tells me? It tells me that the function is concave down, right? Negative 2 means that, negative derivative, we are in a scenario like this parabola here. And so the function will look like this. And is that true? Yes, it's true, right? Because we are in the interval where, 0 is in the interval where we know already that the function looks like this. Now, at the point 1, the function is 3 plus 2 is 5, minus 2 is 3. The function is positive, right? And so the function looks like that. And again, the graph confirms. And then at the minus 2, it's 3 by 4 is 12, minus 4 minus 2, so again it's positive, and the function looks like that, right?
Okay.
So now we will do, well, I have 1, 2, 3, 4, 5 problems from the book that will do, we'll try to do a number of them. But like I said, I want to leave also some space and time also for doing implicit differentiation, because the result of the test were not encouraging, to say the least.
So by finding those points, that's pretty much where the slant is changing.
Yes, it's absolutely. So the derivative stops from goes from being increasing to being decreasing, and so it's not the slope. The slope changes at the. The slope of the derivative goes from positive to negative at the critical point. It's the twist of the function, the curvature somehow. Yes.
Knowing where the function increases and decreases can tell us that, right? Or
it gives us an indication, but you don't know exactly where it transitions, right? Because see, the function is increasing all the way from here to here, but you would not know that at the point minus 1 minus square root of 7 over 3, the function changes from being concave up to concave down. But it gives you an indication, yes. And if you make a mistake, if your graph is well, if you do the graph right, the first derivative and second derivative have to give you complementary information, not conflicting information, right? So that is very important. So, all right, so we'll do a number of examples. that will clarify this, notion even more. So let me start. Okay, so what do I have here? I have a cube root. Oh, beautiful. So I have f of x equals to the cube root of x squared plus x plus 1. So you know that the cube root is always defined, right? So you don't have a problem of, the argument of the cube root can be positive, can be negative, right? It doesn't really matter. So we want to sketch. So what am I asking you? I want to ask you to find the critical points, the interval where the function f is increasing or decreasing, number 2, the inflection points, and the intervals where the function is concave up or concave down. Actually, for this function, we do all of these. Well, we'll see whether we can. So let's say the following. For now we do just the first 2 parts, and now we sketch a graph of the function. All right. So this part we put on hold because I'm not. I should have written down what the problem asks exactly here, right? Anyways, let's, to answer the first 2 questions, you do need the first derivative, right? So you need to see where the derivative is 0. So when we do the derivative of cube root, the whole thing to the 1/3, right? So x squared plus x plus 1 to the 1/3. So when we do the derivative, we apply the chain rule.
So it's 1/3 times x squared plus x plus 1, the negative 2/3 times 2x plus 1.
2x plus 1. Very good. All right. Now we have to, if it was like a problem on derivatives, that would be fine. But now, remember what I'm asking you to do, right? We have to see where the derivative is equal to 0 and where the derivative is positive or negative, right? But I'm not just asking you to see where the derivative is 0. I'm asking you to find the critical points. And the critical points are the points where the derivative is 0 or does not exist. Remember? So it means that there may be critical points then where than you think there are. So let me be more precise. The function with a negative exponent is at the denominator, right? So that means that I can rewrite my function as 1/3 times the numerator, and the numerator can become 0, right? If x is equal to -1/2, the numerator is 0. But then we have x squared plus x plus 1 to the 2/3, and can that guy be 0? Well, if the guy is 0, then we have a problem, do we? Or rather, we have a critical point, right? The points where this thing is 0 are the points where the derivative does not exist. And if the derivative does not exist, then it's still a critical point that we have to talk about. But we are lucky this time. because, oh, by the way, oh, yeah. Okay, guys, have you copied that?
Okay. Okay.
3.6, 4.1, and parts of 4.2. So 4.2 is about the critical points and sketchy graphs of polynomial. But there are also parts, i.e. the second derivative test, that I don't want to do now, not to overload you, and I will do after the test, right? So you can, if you are familiar with calculus 1 already, I know that some of you are taking this class for the second time. You want to use the second derivative test in the test, use it. But if not, you decide about the critical points as I will show you in class now. Okay. So I'm not going to cover, like I said, the second derivative test yet. We'll do that next week. All right, critical points, the interval where f is increasing or decreasing. And so now we have to decide whether this guy can be 0. So can x squared plus x plus 1 to be 0? And if it's 0, then we have critical points. If it's not 0, we do not have critical points, right?
Mm-hmm.
So how do you answer to this question?
Equal to 0?
I'm sorry?
You know, that it equal to 0?
Yeah, we said that equal to 0, and what do we do now?
So,
All right, we try at least, right? You want to factorize the guy, you don't know how to factorize this guy, right?
Mhm.
So let's jump on the quadratic formula. B squared
Minus 4 times 1.
minus 4, right? Divided by 2. So we are lucky there is no other critical point, so that is no solution, right? Because
This is
the
negative.
square root of minus 3
It's not exact.
is not defined, right?
All right.
So it means that the argument of the square root is always positive. So the only critical point, so the answer here to this question is no, and happy we are. And the only critical point can come from 2x plus 1, right? So we solve 2x plus 1 equals 0. So that means that x equals to negative a half. And now if we do our favorite graph, well, it's, that's a very simple graph, right? Because it's an equation of degree 1. But, you can take the test point if you want, right? If x is equal to 0, then it's positive. If x is negative, etc. Right? So it's a graph that looks like this, right? Because here is negative and here is positive. Okay. So let's sketch the graph of this function. Again, starting from the critical point, right? So the critical point is at negative a half. So we can plug the negative a half into the function. And we get 1/4 minus a half plus 1, right? So 5/4 minus a half will give us 5/4 minus a half will give us 9, and that's a cube root. Yeah, will give us 9/4, right?
Oh. Give us 5 over 4 minus 2.
Would it be 3/4?
Yeah.
maybe 3/4.
5 over 4 minus 2 over 4.
3/4.
Oh yeah, that's right. It's a 3/4. See what am I doing
so with the
three-quarters.
Okay. That's,
Yeah, I was doing the common denominator. So anyways, so that is the value of the minimum, right? The relative minimum. And the function looks like this. Looks like a big parabola, right? Right?
Yes.
Right, is what it is, right? So the point is a relative minimum, and there is no relative maximum or inflection point that comes from the first derivative. Let's see how the second derivative looks like, right? So now, if you guys calculate the second derivative, you have to start from, my recommendation is to start from the simplified version of the first derivative, right? If you want to use the product rule, you can use this version. If you want to use the quotient rule, you can use that version, right? And let's see how the second derivative looks like and whether we can easily solve it, right? So, so the picture seems to indicate that the function doesn't have inflection point, right? It seems like if it's a big parabola, but maybe we are wrong, right? Maybe the correct graph will be something like, remember that is, it has to go the right way, right? So it would be something like this, right? Maybe, who knows, right? And maybe the point of maybe there will be some transition point where the function changes its, but let's see, let's verify that. All right, so who wants to give me this second derivative? All right, 1/3 is out for everything, for every term.
it's going to be 2 over 3.
Okay.
Times x squared plus x plus 1.
To which
Should
power?
be, negative 5 minus 3.
Uh-huh.
And then you have to multiply by 2x plus 1.
Uh-huh.
And then times 2x plus 1 also. Because it's the product rule, right?
Mm-hmm.
So you have to multiply by 2x plus 1.
I did it.
But plus, that's a chain rule. There's the chain, isn't there the chain rule?
Oh, yeah, of course. Yeah, I'm sorry. So that will be a square then.
And then plus,
Plus.
it's the term on top.
Okay.
So 1/3
Mhm.
x squared plus x plus 1
Mhm.
times 2.
Times 2, right? All right, so you have copied that, so I better dispose of this list. So times 2. All right, and now we do an excellent exercise of factorization of the lowest power of this term, right? So the lowest power is minus 5/3, right? So because now we have to simplify, right? So we have to set that equal to 0.
Why is that squared?
Because it was 2x plus 1 from the chain rule and 2x plus 1 from the product rule. So there's two
Right.
2x plus 1s.
When we apply the chain rule, we get a 2x plus 1 from here, but then 2x plus 1 from there, right? So that's, if that is f, and that is g, all this thing together is f prime, and then there will be a g, which is, 2x plus 1, right? That will be a g. And now we have f
If you're
prime.
multiplying it, you're not squaring
No,
it.
you have to cancel 1/3. That's f squared.
Mhm.
You can cancel 1/3.
And now we cancel a lot of stuff, right? We cancel 2/3 in fact, because we have a 2/3 here and 2/3 there, right? But no, Alex is right. It's best. Remember that now we can ignore the terms that we don't need. So the constant 1/3, you know, we can avoid, you know, taking it with us because that's not gonna come. But you know, I don't want to give you ideas. You know, I don't want you to simplify things that eventually you can't. So for now, I just want you to simplify. I mean, to factorize the lowest power of this term, right? Of the term x squared plus x plus 1. So we have x squared plus x plus 1 to the lowest possible power, which is -5/3. Right? And then what? What do I have after the factorization?
-2/3.
But how would you solve this equation?
Oh, okay, I get what you're saying. Okay.
How are we solving
Oh,
this
so
equation?
you're
That's
taking
what
out-
I'm asking.
Oh, I get it. Okay, okay. So you're saying you're gonna be left with 2x plus 1. Well,
Times 2x
okay.
plus 1.
Yeah.
Yeah, okay.
Okay, I got it. Yeah,
All right. So, all right, we have to solve this equation, right, and not make mistakes.
No, I'm saying in the top, I meant you're gonna be left with a 2x plus 1 squared plus a 1. Well, if you factor it out.
Mhm.
Well, also the -2/3.
Right.
-2/9 if we don't cancel 1/3. If we cancel 1/3, we
Yeah,
have
-2/9.
-2/3, right? But let's not cancel just yet, right?
Okay.
Mhm. Now we have here plus. If we
Yeah.
factorize the power -5/3, we are left with what?
Yeah.
3
one is-
over 3?
Yeah.
3/3, which is 1, right? So we are left with x squared plus x plus 1
2.
times 2/3. By the way, a few of you have noticed a -1 in their quiz because of the lack of parentheses. Right? So you might want to make sure, especially in this problem, that all the parentheses are accounted for, right? So
Factorize using the lowest exponent.
I do factorize using the lowest, right? Because I want to have a polynomial. Remember, next thing I want to do is to set it equal to 0. So this way, this term I don't care for because I've already verified that it's never 0. So this term I can cancel, right? So this term I can cancel because it's never 0. So I'm left with this stuff here. Now we factorize also 2/3, or 2/9 rather, if you prefer. And now we see what we have, right? So we factorize 2/9. And so we have minus 2x plus 1 squared plus 3 times x squared plus x plus 1. Right?
So you want to like multiply everything out?
Yes, and now we want to clear up everything. Questions? From here for this guy, 1, right? Because that is
3 over 3.
minus 2/3 minus 5/3, right? So the minus 2/3 plus 5/3 is 3/3, which is equal to 1. So we will see this trick a lot, especially when you have, this problem is in the book, so that is one of the, problems given by the text. But there are others with the square root. We're going to do all of them.
It can cancel out because that will never equal 0.
That will never be equal 0. So I don't care, right? As well as I don't care for the 2/9 because there's no, it's a number, right? So I can cancel. And now I solve the remaining expression here, right? It's minus 2x plus 1 squared plus 3 times that equals 0, right? So now let's simplify this expression. So we have what? We have a minus 4x squared plus 1 plus 4x with a minus, and then we have a plus 3x squared plus 3x plus 3, right? So we have a what? Minus 4x squared minus x minus 1, I'm sorry, minus 4x plus 3x squared plus 3x plus 3.
Professor, can you explain really quick? Sorry, I'm just not seeing it.
What?
The factoring of the 2 9 to get the 3.
The same
Can you put
story.
it in like fraction form really quick?
Sure, absolutely. So I'm factorizing the 2 9s, right?
Okay.
So let me do the, without writing down all these numbers. So I have 2 9s times something, right? No, it's a minus 2 9s rather, right? Plus 2/3 times something else.
Right.
So I want to factorize the 2 9s. So I have the 2 9th times minus something.
Right.
And now I have what? I divide by 2 9s, right? So I have 9 over 2 times 2 over 3 times the stuff.
Oh, okay.
Okay, so when I factorize, I divide by.
Yeah. Yeah, I got it. Okay.
All right. So I have 3. So here I have what? Let's see. So 3x squared and 4x squared is minus x squared. Minus 4x plus 3x is minus x. Minus 1 plus 3 is plus 2. So I have this guy here. And surprise, surprise, this guy is going to give us zeros, right? So let's calculate the derivative. So now, I'm sorry, we have to sacrifice some of these definitions. All right, so we want minus x squared minus x plus 2 equals 0, right? So we can set, change the sign to everything, if you like, and write it like that. So again, the quadratic formula, minus b plus or minus square root of b squared minus 4ac.
4 times 1 times -2.
So that would be an 8 divided by 2. Well, actually, that can also be factorized fairly easily, right? X minus 1 times x plus 2. But, we do the quadratic formula. So when x is, when the sign is a plus, we have minus 1 plus 3. So we have 2 over 2 is equal to 1. When the sign is a minus, we have minus 1 minus 3 over 2, so we have negative 2, right? So these are 2 inflection points, right? So minus 1 and minus 2 are inflection points. And from this graph, right? It's you can see what's happened, right? At minus 1. The function changes, right? It's from concave up and then it goes concave down, even though it's still increasing. So it goes.
So these are inflection points?
Uh-huh.
But you're only going to have. But how is it? Because the way that, I see that blue graph, wouldn't there be, 4 inflection points? Or...
No, because the graph still continues to decrease.
The graph still continues to decrease, right? But this graph is not correct, in fact.
Oh, but
right?
that's what I'm saying. If we were to go based on that blue graph, there would be technically 4.
That's right. No, the blue graph, in fact, is not correct, right? So it looked like, see, that is why the second derivative is important, right? If it was just for the first derivative, we could say, oh, it's a big parabola. It's not a big parabola, really. Right? Because, okay, at minus 2, we have the first inflection point, right? So, and the function, it's you know, it still goes to infinity, but it doesn't go to infinity like the blue graph said, right? So it goes to infinity like a square root, right? So it goes like that, and then there is a transition, right? And then there is another transition. The graph still goes to infinity, but now it goes more like that.
This is 2 inflection points.
Mm-hmm. That's right. One is at -2, and the one is at 1. So see, we had just gone with the first derivative, we would have thought the graph is a big parabola, but now it looks like if it's a bit more complicated than that, right?
So does that also tell us about, like, you know, the concavity?
That's right. So now the question is, where is the function concave up or concave down, right? So from the graph it's clear that in this interval the function is concave down, that is concave up, and that is concave down. But so that is our f second, right? That is our second derivative here. So now and we have found the zeros of the second derivative, which are at -2 and 1, right? So the graph looks like this, -2 and 1, right? And you know, now remember the second derivative is -x squared minus x plus 2. So now, how do we study concave up, concave down? We pick up test points and we plug them into the second derivative, right? So we can pick up the point 0, we can pick up the point 2, and we can pick up the point -3 if you want, right? So if we plug in 0 into this function, so we get 2, right? Is equal to 2, so that's positive. And now we are talking we are talking second derivative here. So a positive second derivative means that the function is concave up, right? If we plug in 2 into the second derivative, we get -4 minus plus 2. Oh, I'm sorry, I must have made a little mistake here in the calculation of the inflection point. Because one of the inflection point is 2, and the other is yeah, there is a minus here and there is a plus there, so that is a -1 and that is a +2. Yeah, because I mean, if you plug 2 into this, if you plug 2 into here,
You get
right,
0.
then you get -4, -4, 0, right? So, no, wait a moment.
Wait.
No, that is actually correct, because if plug in 2, we get -4, minus 2 plus 2, 0. 0 here, but yeah, the result is -4, it's not 0. Okay, hallelujah. So sometimes, you know, it's this little tedious algebra that is the most annoying of all. And -3 is finally what? -9 plus 3 plus 2, so it's again -4, and that is negative, right? So, okay, so what is the answer to this problem? So the answer to the problem is that f, so the final answer, so critical point, only x equals to 1/2, right? That's the only critical point. Now, f is increasing for x greater than 1/2, decreasing x less than 1/2. Inflection points are at x equals to 1 and x equals to -2, concave up at x between these two critical points, and concave down at x greater than 1 and x is less than -2. So you can write the solutions in interval notation if you like, but to me that is absolutely fine, right? Okay?
Is it a -1 now?
No, it's not right here. I thought I was making a mistake, but I was making a mistake in the test points. So no. That's +1 and -2 as it should.
No, in the original proof.
The original critical.
Yeah. The inflection points. No, the critical point is 1/2.
No, it's -1.
-1/2. Oh, sorry.
Thank you.
All right, let's so I would like to do at least another couple. Okay, so let's do another problem with fractionary powers.
Was there then an equal, well, were this critical points x equal?
Equal, yeah. Yeah, x equal. All right. So, we do the same thing now for another function, right? So this function is gonna be f equals to x to the power 5 cube root minus 15 x square cube root. And again, we want to find the critical point, the intervals where the function is increasing or decreasing, the inflection points, etc., right? So now, for this function here, we do the whole thing. Now, for the next functions, we do only increasing or decreasing, etc. All right. So first of all, when we see the square roots, the root symbol, we want to eliminate them, right? So we have x to the 5/3 minus 15 x to the 2/3, right? All right. Now, who wants to give me this derivative?
That's just 5x.
There. Okay. So that's the quadrant that always answer.
Yeah.
Yes, I was about to ask for somebody in this quadrant as always, because that's the quadrant that never answers. All right. All right, 5/3 x to the 2/3, very good. Minus, okay, so because we have 15 times 2/3, that simplifies into -10. And then we have x to which power? So 2/3 minus 1 is -1/3, right? So let's simplify the whole thing. So we have 5 here we simplify, 15 and we have 10.
Mhm.
So we can factorize a 5. And then we have x to the 2/3 minus 2 times x to the negative 1/3.
Okay.
So now, again, we have a negative power, right? So if I ask you to solve the equation and to give me the critical points, you have to keep in mind that this negative power goes at the denominator, right?
Yeah.
So before you start answering, we have to dispose of it, right? So we have to keep that into account.
Is this supposed to be f of x on top?
It's x
Mhm.
to 1/3.
Yeah, that is f of x,
Okay.
right?
Can we put out the 5?
This is f prime,
we pull
right?
out the
This is the
5. That's
derivative.
2/10. That's
So
Okay.
now I want to
Okay.
set that equal to 0, right? So
Mhm.
I want to write that, there is the 5, not that we can, eliminate because, 5 is superfluous. But the rest of the stuff, it is not superfluous, eh? The x to the 1/3 here. So when I do the, yes?
X to the 1/3, it can't be 0. Like, you have to.
X to the 1/3 can be 0 just fine, and now we discussed that. But yeah, let's do the common denominator first.
okay.
So x, if we want to put everything under one fraction,
Mhm.
the numerator is,
Minus 1/3
when we do
times
the common denominator,
1/3.
would just be x, right?
Yeah.
X to the 2/3 times x to the 1/3 minus 2. So we want that to be 0, and the results is equal to 0 if x is equal to 2, of course, right? But then there is the denominator. The denominator can be 0. Why not? Because the function, if I plug 0 into the function, I don't get something impossible, right? The function is 0. The derivative does not exist. Now we have to talk about that, right? So it's 0 if x is equal to 2 and does not exist if x is equal to 0, right? The derivative does not exist because it makes the denominator equal to 0. So the critical points are 2, x equals 2 and x equals 0, right? So these are 2 critical points. Oh, it can be equal to 0 just fine. Again, we're talking about,
X
then
minus 2 over
eventually sketch the
1/3,
graph of
okay.
the function. The function is defined at x equals 0. And now we have to wonder what's happening if the derivative is not defined, right? And now we'll talk about that in a moment. So, but for now, let's find the intervals where the function is increasing or decreasing, etc., right?
So we plug in a 1,
Test points, yeah,
-1,
And 3.
and 3, right? We can plug all of these points because the cube root is always defined, right? You can take the cube root of anything. So the derivative, remember, actually better write a clean expression for the derivative, right? F prime of x is equal to 5 times x minus 2 over x to the 1/3, right? And that is it, right? So when we plug in x equals to 1,
Okay.
we have 5, which we don't care for, right? 1 minus 2 is minus 1, right? So remember, we have kind of disposed of 5, right? Minus 1 over 1, so
Minus
negative 1,
And plus
which
6.
is negative, right? F prime of 3 is
1 over
cube root of 3
is greater than 0.
is greater than 0. We don't care what it is, right? F prime of minus 1 is
Negative 3 over
3 over
cube root of negative 1
It's gonna be less than.
is gonna be positive, right?
oh wait, square root of
negative 1 to
oh
negative 1.
yeah, okay, no.
The square root would be a problem. The cube root is no problem, right?
Yeah.
So it means that at 1, the function is negative, so it goes down. At minus 1, the function is positive, so it goes up. Right? Then it goes down. Right? And, no, I'm sorry. At minus 1, it goes up. From at 1 is positive.
One goes positive.
All right, yeah, so see, it's always best to have the points in order, right? So at minus 1 is positive, at 1 is negative, and then is positive again, right? So at 1 is negative, and then is positive again. So see, at 0, the interesting things happen, right? At 0 is actually a relative maximum.
You can never have like either way.
What do you mean?
If you start making that and you get 2 going up, then you know that you did something wrong, right?
No, you don't know.
Like in the sense of like
You don't know, because I mean, if you consider f of x equals to x to the third, right? And if you do the derivative is 3x squared, right? Is equal to 0 if x is equal to 0, right? So if you, that is your critical point at 0, when x is negative and when x is positive, the derivative goes up. It just means that you have an inflection point, right? You have a critical point which is not a maximum nor a minimum. When you have things like that, it means, and if you have done the calculation right, it means that this is an inflection point. You can have that, right? But I was checking to make sure because I suspected that there was an inflection point here. There is. So, okay, so that is the situation then, right? So the point 0 is, all right, so let's answer first the first question. So the critical points are x equals to 0, x equals to 2, right? So what is a relative maximum? So which of these points is a relative max?
0.
0. Relative minimum? 2. And f is increasing where?
Negative infinity to 0.
Negative 1.
2 to positive infinity. And decreasing
Between 0 and 2.
between 0 and 2, right? So now we study the convexity and, concave up, concave down. But first, let's sketch the graph and let's try to understand what's going on at the point 0. Because the point 0 is kind of mysterious, right? The function is defined, but the derivative seems to be kind of weird because the derivative does not exist. So let's do the graph. Right? And the critical points are at 0, and as always, we start from the critical points. So f of 0 is equal to 0 because, the fifth root, the third root of the 0 is 0, etc.
Does it matter if we use brackets because it's I don't know, like because it's including the point 2, like for f increasing and decreasing?
No, it doesn't include the point 2 because 2 is a stationary point. Right?
Oh, okay.
So I mean, that's not the type of error that I yell at. But if you want to be absolutely correct, you don't include the critical points because critical points are stationary. The function doesn't increase or decrease or anything. Right? Now, at the other critical point, so the point 2 would be what? 3 times the cube root, so 2 to the 5th is 32, the cube root of 32 will be the cube root of 32 minus 15 times the cube root of 4. So if you want to bring out the 32, we want to take out 8 out of the cube root. So then it would be 6 cube root of 4. When we want to take out 16, not 16, I want to take out 8 out of the cube root, right? 8, 32 is 4 by 8. The cube root of 8 is 2. I
Okay.
can take out the 2
Okay.
from the cube root,
Mhm.
right? 2 by 3 is 6. Mhm.
So negative one.
So 6 cube root of 4 minus 15 cube root of 4. So that's a negative value. That is 7. No, minus
No.
8.
Negative 9.
9.
No, minus 9, sorry. It's cube root of 4.
Okay.
So minus 9 cube root of 4. So at 0, the function is 0. And at 2, the function is, this value here, like minus 9 cube root of 4. All right, so now how do we sketch the function, right? So the function goes through this point and through that point, right? Now, answer my question. When x goes to plus infinity, the function goes to where?
Positive infinity.
Positive.
Does this increase?
Because it goes to positive infinity, right? When x goes to minus infinity,
Negative.
negative infinity, right? So maybe there's some mistake here. I think that, hold on. So when x goes to, all right, so we have to decide what's happening at 0 here, right? So when the function, the function is defined, it's equal to 0, right? So it is coming from minus infinity and it goes up, right? Up. Now, when, minus infinity means, I mean, the derivative is not defined, right? And when x approaches 0, the derivative goes to infinity somehow, right? Minus infinity to the right and plus infinity to the left. So when what does it mean for the derivative to go to infinity? It means that the function becomes steeper and steeper, right? Because the slope goes to infinity of the tangent line. So a line with infinite slope is a vertical line. So it means that the function, it's, yes, it will be very, very, very close to the y-axis. So it will be, it will go to 0 like that, right? Right.
But why?
No, it won't touch. Oh, it won't touch your right because
Okay.
the function is defined.
Okay.
The slope is infinity. The slope goes to infinity. It means that
Okay.
the function, it becomes vertical, right? It's it gets really steep near 0.
But it touches.
It does touch 0 because I can plug 0 into the function.
But how do we know that that it does that?
Oh,
again?
it's different, right?
Explain that.
Because the derivative is not, the derivative means the slope of the tangent line. So at 0 there is no tangent line. there is no slope, right? And when x approaches 0, the slope, which is the value of the derivative, is x minus 2 over x, right? So when x becomes really small, the value of x minus 2 over x becomes really large. So when x approaches 0, the slope of the tangent line becomes really, really bad, really, right? Really big. Up to when, when it gets to 0, the tangent line is vertical, right? So the function looks like this, and then on the other side, same story, right? When it approaches 0 from the other side, again, it will become vertical. So near 0, the function looks like that, right? Instead of going to, to 0 in a nice round manner, it goes with a cusp. It has a cusp at 0. Yes?
If, like, maybe we didn't know that it looked like that, could we find that out by checking, like, the second derivative and then changing the graph to turn like that?
Oh, yeah, definitely. You can check the second derivative, which actually is not so bad, right? The first derivative looks more intimidating. Now we can do the second derivative, and the second derivative will confirm that the function is concave up here and here, right? And so therefore the 0 must be a point, some kind of strange point where the two concave up paths meet. And so that's how it is. Yeah, and then also this is the maximum, and then it goes to infinity like this. So that's the graph of the function. All right. So I really wanted to do these problems with the square root because they are among the recommended problems, so they needed to be done. But now I promise that the next examples will be easier. I mean, this is easy. I mean, this is just algebra simplification, but the derivatives altogether are not easy, are not difficult, right? All right, so we can do also the second derivative if we want to finish this problem, but I'd rather move on to another problem so as to give you a variety. Yes? You guys are tired, I know, take a deep breath. Come on, the test is Friday, we have to do problems, not problems before Friday, right? So, all right. Again, do you want me to do the second derivative, or you are okay, or you want to see another problem?
Yeah, let's do it. Another second derivative. Do it.
Second derivative.
Another problem, raise your hand.
What?
If you want to see another problem, raise your hand. If you want to see the second derivative, raise your hand.
Second derivative.
Sorry, the other problem wins. I can show you the second
Some people
derivative.
didn't vote, I'm just saying.
I can show you the second derivative after class if you want it. Okay. So we'll keep the second derivative in here. Okay. All right. So here you've seen cases where the critical points are points, remember, where a prime is equal to 0 or does not exist, right?
Okay.
But there are cases of critical points which you exclude from the very beginning because you know already that the function, because you know that the function does not exist, and so if the derivative does not exist, and you don't care anymore at this point. So let me explain what I mean by that. Suppose that you consider the following function. So f of x equals to x squared over x minus 1, right? So now you have problems that you didn't have before, right? The function that I gave you with the cube roots was defined everywhere. But this function here is not defined at x equals to 1, right? So x equals to 1, it doesn't, you know, the function doesn't exist, right? And if you do the limit at this point, the function looks like, you know, 1 over 0, so clearly the function is going to go to infinity at that point, no?
Yeah.
So now let's do the usual thing, you know, critical points, blah, 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 blah. So who wants to give me the derivative of f?
2x
2x
minus
2x
x minus 1
Mhm.
minus 1 times x squared. Minus x squared.
Very
Over
good.
x minus 1 squared.
X minus 1 squared, right? So we have again a fraction, right? Now it's an easy fraction. I mean, we didn't have to pay and suffer like before. So we have what? We have 2x squared
Minus 2x.
minus x squared, right? Over x minus 1 squared. So we have x squared minus 2x over x minus 1 squared, right? So now, like before, you know, we had a fraction, and so we had to study the numerator and denominator, and we do that too, right? But now the denominator has no surprises for us, because x equals 1, you know, we know that the function doesn't exist, so if it doesn't exist the function, it doesn't exist the derivative, right? So x minus 1 we don't care for, x equals 1 we don't care for anymore. We do care about the numerator, right? So we study the function x squared minus 2x equals to 0. So we factorize x, and we find out 2 points, x equals 0, x equals to 2. And these are our true critical points, right? These are critical points. The point 1 is I mean, the derivative doesn't exist, so call it critical points if you want, but that is not going to be interesting for us because the function is not defined at 1, right? So 1 is a point where the function does not exist. So here, you know, x equals to 1, the f of x does not exist. I mean, f of 1 does not exist, and also f prime of 1 does not exist, right? So it's you know, it's a point which has no surprises, so it can't be considered a critical point. I mean, like the others, right? So all right, let's okay. And now here is another thing that we can observe for this function. So let's see whether you know, points 0 and 2 are relative maximum, relative minimum, blah blah blah. Remember that at 1, so here is the bad point, right, where there is like an asymptote, right? The function doesn't exist at this point. So we need to pick up some other point to do our test. So, for example, if we pick, say, the point minus 1, then what? Or we pick the point 0.5, or like 1/2, or we pick the point 3. So then we see the f prime minus 1 is equal to 1 minus 2,
minus 1.
because it's minus is plus 2,
Okay.
right? So it will be positive. Now, the denominator is always positive. I don't care for the denominator, right? When I do these considerations. So I can, you know, ignore what's going on down here because it's going to be always positive. So, but anyway, so f minus 1 would be equal to 3 over 2 squared, right? But I mean, again, that's not going to change anything, you know, the denominator, because it's going to be positive. Anyway, that's positive. So f prime of 0.5 is going to be equal to 0.5 square minus 2 times 0.5 minus 1, 0.5 minus 1 squared. And so it's going to be negative, right? Right.
Okay.
And finally, f of 3 is equal to 9 minus 6 over something. It's going to be positive, right? So the function is increasing. It's decreasing, but now keep in mind that we have an asymptote in here, right? At the point 1, the function goes to infinity, right? So it's decreasing and it's decreasing again by the asymptote, because there is an asymptote here. And then it's increasing. Okay. So now let's sketch the graph of this function.
So do you assume that it's decreasing, like on the right side of the asymptote?
Oh yeah, because I do, right? Because I mean, I plugged in the test point, it was giving me a negative value. So across the, if we go on the other side of the asymptote, nothing is going to change, because x minus, I mean, the only effect that minus 1 could have is on the denominator, which is always positive, right? If you want to verify that, you can plug in like 1.5 into the function and verify that it is still negative, right? 1.5 square minus 2 times 1.5 will give you negative. Will give something negative. So anyways, alright, so let's see how is the story. So remember that at 1 we have an asymptote, right? At 1 we have an asymptote because the function goes to infinity, near 1. Now, the point 0 is a critical point. The value of the function at 0 is 0, right? The other critical point is at 2. The value of the function at 2 is 4. So we have a 2 and we have a 4, right? All right. So now 0 is a relative max, right? And 2 is a relative mean. And there is an asymptote in between. So, do you want to try to sketch the graph of the function? Oh, wow, it's already 5:41.
Okay.
Well, sorry, not enough time to make experiments. Yes, so we go all the way up, right? All the way down, right?
All the way down and then from the
All the way down, yes. And now we start at plus infinity, we go all the way down up to the minimum point,
back up.
and we go all the way up, right?
Okay.
And just to check that we are doing good, the limit as x goes to plus infinity of this function by the garbage rule goes to plus infinity, and so we are good, right? And minus infinity is minus infinity. So just to make sure that, the limits, if the graph will tell us something else, it means we are doing something very wrong. Okay, so guys, if you have some questions for me, now I'm kind of taking over the office hours that Jason had. So, you know, if you have questions, don't hesitate to ask. I can stay a little bit longer. Yes.